Okay, third and final video, I promise. So we got a few things, terms to go over, couple more examples to reinforce potential versus potential difference, and the types of questions that you could get on a quiz or a test or a CUME or the diploma, and then equipotential lines, couple practice problems, and we'll call it a day. All right, so electric potential, I've been going on and on and on about. Electric potential and electric potential difference is the same thing. Both of them has the variable delta V or just big V, and the units are the volts. Fine. Then we're talking about this electric potential difference again being the same as electric potential and being measured in the volt. The potential or the potential difference all has to do with the amount of distance or voltage that something will pass through on its journey. And we measure that by, again, the difference in the amount of potential between two different positions, which we just talked about. As a formula, electric potential is the change in potential energy per unit of charge. And we described it the same way with gravitational. We said that gravitational potential energy is mgh, and the potential is the amount of potential energy per unit of mass, and that would be specifically height dependent or position dependent. This is the amount of gravitational potential something has. That would be gh. In the case of electrostatics, we say that something's electric potential energy is the product of its charge and the amount of potential or potential difference it will pass through. The amount of potential then is the potential energy per unit of charge. So that is the potential measured in volts. And again, it is position dependent, not so much in distance, but how much potential difference or voltage will something pass through on its particular journey. And the journeys could look different depending on whether or not you get a positive or negative charge. And that's what you have to wrap your head around. So a couple more examples with this. And I really mean a couple more, promise. I'll do this one. Let's make the top plate negative in this case and the bottom plate positive. And let's say that you've got two particles again. One of them is a proton, and it is sitting down here. And the other is an alpha particle, and it's sitting down here. Now, if you look on your formula sheet, the alpha particle has a charge of positive 2 electron volts, or sorry, positive 2 elementary charges, and the proton has a charge of 1 elementary charge, and that is on your formula sheet. You need to look at them because I'm going to be using the term alpha particle and the particles, alpha particles, quite a bit. So the question is, who has greater potential energy and who has greater potential or potential difference? And to do potential difference, you need to look at its journey. So again, potential is the product of its charge. Sorry, potential energy is the product of a particle's charge and the amount of potential difference it will pass through on its journey. Now, both of them, because they're positively charged particles, will move in this direction. And if we had this connected to a 100-volt battery again, we would say that both of them will move through 100 volts of potential. They're going in the same direction, and they'll pass through the entire distance or the entire potential difference on their journey. So this is the same or constant for both. The alpha particle will have twice the amount of potential energy as the proton has, so this will be bigger, and that's because, not because the potential is more, but because the amount of charge is more. So your proton will have a charge of a single elementary charge, and it'll pass through 100 volts of potential. So its potential energy will be 1.6 times 10 to the negative 17 joules. That's for your proton. The alpha particle has double the amount of charge. So to calculate its potential energy, its charge and its potential or potential difference again will be multiplied together. The alpha particle has a charge of 3.2 times 10 to the negative 19. That's on your formula sheet, so double the charge of a proton. It will also pass through 100 volts. So the amount of potential energy that it has is is 3.2 times 10 to the negative 17 joules. So your alpha particle has double the amount of potential energy, but the same amount of potential difference or potential, because they will pass through the same amount of voltage on their journey. So this is the same. And your potential energy is doubled in the case of an alpha particle because of the double amount of charge. Position, same, charge, different. Let me see if I do have some space down here. Okay, and one more example of this, again with position. So I'm just going to give you a single charge particle this time. So let's say that we have a field that is caused by a positive source charge. And let's say that we've got, we'll go with a proton. So again, a proton is a nucleus of a hydrogen atom, so we can isolate those. This is not quite the same thing as when charges move or don't move in the case of friction. We can isolate this single proton and stick it here around this source charge. Now, if this proton is position A, then the question is that if we were going to move it, the same particle, same proton, to position B, would that proton possess more potential energy at position A or less potential energy at position A? Okay, so it's the same particle, and we're talking about potential energy. So this is the constant. This is your proton. Now, where does it possess more potential energy would depend on how much potential difference it would pass through on its journey. So we got to look at this. Where does it naturally want to go? And if your proton is sitting here at position A and you are holding it with your particle tweezers, when you let go of it, it would head out in that direction. And in doing so, it would pass through all of this distance. It's going to keep going, but it's going to pass through all of that distance or all that potential difference on its journey. And the potential difference is created by this source. Now, if we put our proton at position B, then it will still move in this direction, of course, because it wants to get away from the like source charge. And in doing so, it'll pass through this much potential difference. So we would say that the proton has more potential energy at position A, and that is because it has more potential difference at position A, because it will go a larger or a longer amount of distance as it's moving, and therefore pass through more potential difference. Now, we could take this exact same scenario, and this is why you can't memorize. If we change the particle and we make the particle an electron, then the scenario is completely different. So again, we have an electron at position A, or the same electron at position B. And the question would be, at which position, A or B, does that electron possess more potential energy? So if we look at it at position A, if we're holding it here at position A with our particle tweezers, at the second that you let go of it, it's going to head in this direction. And in doing so, it'll pass through this amount of distance and a certain amount of potential difference that's proportional to that distance. Now, if we take that particle and hold it over here at position B and let go of it, it's going to travel like this. And that's because naturally it wants to move towards the unlike charge. Now, as it's traveling through all of this distance, it's passing through a proportional amount of potential difference. And so we would say that at position B, we have more potential energy because it will pass through more potential or more potential difference on its journey. So same positions as the previous example, A and B. The particle is different though, and its journey will look different. So you have to not memorize, but ask yourself, where does this guy want to go? And he wants to go this way. Where does he want to go? He wants to go this way. And how much distance or how much potential difference will it pass through on its journey? And I think I beat this to death for now. There's a couple more questions that have shown up over the last few years on diplomas that I'll do a little supplementary video after you've done the practice problems. So it'll just be diploma questions related to the topics in lesson 16, but we'll do that later. Right now, let's do the practice problem so we can get to the math, because the math is easy. Oh, we forgot equipotential lines. Okay, equipotential lines, well, they're kind of fun. And there's rules again about how they're drawn, and so we got to know the rules. And basically they're imaginary lines, and they're meant to show potential difference along a particular line. So the way that they are drawn is that, here we go, you want to draw your field lines first. And so you're going to draw your field lines based on what a positive test charge would do, and then your equipotential lines are going to be perpendicular to your field lines everywhere along the way. And so that's said here. The dotted lines represent the equipotential lines, which are always perpendicular to the electric field lines. Fine. And it's meant to represent a certain amount of potential at a given position. Oopsie. Undo. Okay. So if we're drawing equipotential lines between parallel plates, well, that's the easiest. So we have two plates. We would have, let's say again, 100 volts across the plates, and let's go with 5 centimeters. And so every centimeter would represent 20 volts of potential. Now, in this case, we don't really have to draw our field lines because we can easily see how lines would be perpendicular to them, but we'll get used to the concept. So we would draw our field lines based on the way a positive test charge would go, and they would move away from the positive plate and towards the negative plate. So these are field lines. Our equipotential lines are going to be perpendicular to those, and so this way. And we would draw them equipotential or equal distance, where every one of those lines would represent a certain amount of distance and a certain amount of potential. So I've got here these 4 lines, so I would say each line would represent 1 centimeter of distance, which would be 20 volts of potential. So anywhere along here, if we moved crossways along an equipotential line, it would be at the same position relative to each of the plates, so at the same amount of potential. This guy then along here, we would have another centimeter and another 20 volts of potential. So each equipotential line would represent 20 volts. So then if we say that something moved from this equipotential line to this one, doesn't matter that it's diagonal, it's gone through 2 full equipotential lines from here to here, and we would say that that has moved through 40 volts of potential. Now, where Laura likes to make this fun is she won't give you something like as simple as straight plates. You would get something more like, I'm going to move this up, something more like 2 charges that would look like this. And it would be, we'll draw the equipotential lines around, or in this field around these 2 charges. So again, you would start with drawing your field lines, and your field lines are moving away from your positive charge and towards your negative charge, because that's the way a positive test charge would move if you're placed around the field, or if it's placed around the field. So something like this. Okay, now your equipotential lines need to be perpendicular to these guys at every step along the way. And that would look something like this. Well, this one is perpendicular. And then maybe like, well, that looks nice. Okay, so these guys would represent the equipotential lines. So we would say that a particle anywhere on this equipotential line would possess the same amount of potential difference. And in moving through them, so if again we had each line represents 20 volts, I'm just making that up. If something moved from here to here, it would pass through 20 volts and another 20 volts, so for a total of 40 volts. If something went from here to here, though, it would have passed through no volts because it's on the same equipotential line. And that, again, is something you have to wrap your head around, and something that I will show you how some questions have been asked previously on diploma exams. The equipotential lines around a single source are kind of fun. If this is a single source charge, again, your field lines would be going away from that because that's the way a positive test charge would go. Your equipotential lines need to be perpendicular to that and would represent a certain amount of potential at every position on that line. And so by the same, if we said that each line was 20 volts, if something passed from, new color, let's go with black, from here to here, it's gone through 20 volts. If something passed from here to here, it's gone through no volts because it's on the same equipotential line. If it passed from here to here, it would have gone through 20 volts because it moved from this line to this line. And so that looks a little bit confusing, but that's what it's done. From one line to the next line is a total of 20 volts. All right, now let's do the practice problems. Again, read this section if that was like, what is happening? The math is always easy. All right, 50 joules of work. On your formula sheet, in the very far left-hand corner, there is a formula that looks like this. Work is equal to delta E. Now, in the right-hand side of the electromagnetism section, there's this formula for potential difference as change in energy over, over unit of charge. And what I would like you to do on your formula sheet is draw an arrow from that delta E on the bottom left-hand corner over to that delta E in the electromagnetism part. And really emphasize here that work is this change in energy, and that will be measured in joules. And because you'll forget that, and sometimes you need it on the diploma. Okay, so 50 joules of work is your change in energy then, and it's required to move a certain charge in an electric field. And you want you're being asked for the potential difference. And that would be this formula. Potential difference is your potential change in potential energy divided by the charge. Now that change in potential energy is your work, so we'll divide that up by the charge. The work is 50 joules. The charge is 0.50 coulombs. And when you divide those out, we can do this without a calculator, right, Will? You get 100 volts. So 100 volts of potential difference between the 2 points by taking that work and dividing it by charge. Easy, easy, easy. You will never get a question like that on the diploma. This one, you will work with this type of EP is equal to EK through the rest of the course. So you want to get really familiar with this. So basically what this one is talking about is that you've got an electron. Let's make this the negative plate. This is a positive plate. And your electron is sitting there. You're holding it with your tweezers. You let go of it and it's going to take off in this direction. And as it does, it will pass through 100 volts of potential. Now what will happen is that all that potential energy that it has stored on that side due to its charge and its potential difference will be lost. And that potential energy will be converted into kinetic energy as it travels. And what will happen is on this side, there will be no more potential energy because it will have no more potential difference to pass through, but its kinetic energy will be at a maximum. So it'll be traveling super fast as the potential energy it lost is converted into kinetic energy that's gained. And the way we write that as a formula is the change in potential energy is equal to the change in kinetic energy. Now your change in potential energy as a formula is Q delta V, or QV. That's a big V. And your kinetic energy, your change in kinetic energy as a formula is EK final minus EK initial. Now in this case, it started from rest, it says that. So there is no EK initial, and this formula then looks really pretty with QV, or Q delta V, those two are the same thing, is equal to 1/2 mv squared. And this is conservation of energy. Potential energy lost is kinetic energy gained, and you will use this relationship through the rest of the course. Now what you're trying to do here is get its speed, so you will rearrange to QV over m. This is an electron. The charge on the electron and the mass of the electron will both come off of your formula sheet. And get this out of the way. So 2 times the charge of your electron times the potential difference, which is 500 volts, all over the mass of an electron. This is on your formula sheet. And we're going to punch this out. I'm not going to just sit there and wait for me to punch it out. So we'll punch that out. And I get 1.3252591, blah, blah, blah. I'm going to just write it up here. So I got 1.325 times 10 to the 7 meters per second. So as it lost all of that potential energy, it gained kinetic energy, and it'll hit the other plate going very close to the speed of light. So 1.325 times 10 to the 7 meters per second. Okay. Question number 3, I wrote this stuff in here. I would have told you in class that we no longer require you to get the mass of a nucleus, but I left it here just, I don't know why, but I haven't changed it. So on anything that you're going to be given on a quiz, a test, a cum, you will be given the mass of the aluminum nucleus. And I left it here just to show you how I would calculate it. So this number is your atomic mass from your periodic table. So I looked at the atomic mass. One of the definitions for atomic mass is that it's the total number, or an average of the number of protons and neutrons in the nucleus. So I took that, it's got 26.98 protons or neutrons in the nucleus, and I multiply it by the mass of a proton and a neutron, which I got off the formula sheet. So this is the mass of a completely ionized nucleus. Now for aluminum, I got this off the periodic table also. The atomic number is 13, so if your nucleus is completely ionized, all the electrons have been stripped off, and what you're left with is 13 protons providing you a charge in the nucleus. So our charge then will come from the 13 protons, where each proton has a charge of 1.6 times 10 to the negative 19 coulombs. And that's going to give a charge of our particle. Our particle in this case is the nucleus. And it'll give us a charge of the particle of 2.08 times 10 to the negative 18 coulombs. Okay, so you will be expected to be able to do this question except for getting the mass. I will give you the mass. The charge you're going to have to be able to figure out on your own, right? So get the atomic number off the periodic table, and then use that, the number of protons times the charge per proton, to get the charge. So other than that one extra step, this is the same as the question before, where you've got the potential energy lost is equal to the kinetic energy gained. And this question is also from rest. And it's accelerating through here, so it'll lose all of this potential energy as it falls through that potential difference, and it will gain speed as it gains kinetic energy. And again, this V and this V is different. This V is a big V meant for potential difference, and the little v is velocity. So once again, I will rearrange. And we've already done the work here. We've got the charge of our nucleus as that 2.08 times 10 to the negative 18. And we've got the potential difference, which was given to us, 0.25 megavolts, which is times 10 to the 6 volts. And then divide it by the mass, which again I would give to you, 4.50566. And we're going to punch all of that out. And don't sit there. I'm going to punch it. You punch it. And you get 4804381. So 4.804 times 10 to the 6 meters per second. So a little slower than the example or the last question, and that's just because the particle is a lot heavier when it accelerates through. So it'll lose potential energy, gain kinetic energy, and arrive at the other plate going a super fast speed of that. Okay, you guys should be able to do the bulk of the hand-in assignment pretty easily. Question number 8, I will do in that little supplementary video, not today. I'll make it for you for tomorrow. And this one is one of those ones that comes up every couple years on a diploma and you're due for it. And so try it on your own. Don't look at the answers. See if you can figure it out. And then in that little supplementary video of types of diploma questions, I will do this one for you. Okay, that's it for lesson 16.